Hi, I am Dallas Blackwood, and this is my FEA project for the summer of 2026. My project is an automated Python script that develops a Abaqus model from a URDF file. A URDF file, in this URDF file, it has the robot description and how linkages and connections or joints are connected to each other. So for my script, my plan is to parse these URDF files, create parts from them in Abaqus, assemble them, add boundary conditions and loads, and mesh the parts to have a fully functioning simulation through a Python script. Model here in a URDF viewer, basically you can see it can only rotate in one plane. From that URDF file, we have a URDF reader that takes the tree structure from the file and creates a URDF data structure that can be used in the Python script. Our global constants here are the material properties, the material property, structural steel, that we're going to apply to all linkages. There's the mass properties for the point mass that we're adding to the end of the linkage. Instead of having an end effector like a claw or some type of manipulating joint, we're just applying a point mass to the end linkage. I jump down to the main section of the code. After taking in the path for what URDF file you're using and setting up the Abaqus environment, it interprets the URDF file and then returns back the data structure that this robot model that is from the URDF file. So this is the create URDF Abaqus model function. Everything that happens in here is essentially what you're going to do in Abaqus manually. So we start with creating the model itself, giving it a name. It pulls the name from the URDF file. It deletes the predefined model that's already in there, model number 1. Then it creates the material properties. And in this case, from the global constants, we have the material property structural steel. Then it's going to go through our data structure and it creates a root link with a reference point. Because this is a discrete rigid model that's going to be fixed, it takes the root link or base link, fixes it in place with the reference point, and then we'll go through every linkage. In this case, it's just going to be one, and creates a part for each linkage. It computes the positions of where those linkages are going to be based on that URDF file positions, and then it ties those positions together in the assembly instance. For the joints, there's no physical like 3D model for the joints. We're using Abaqus's connector elements to define those. So here we're taking the joints. We're going to only have one. It's the joint between the base link and the one arm linkage that allows it to rotate in one plane. So this is creating that connector. Essentially, it's just creating the joint connector and making sure to find the right linkage to connect it to. So once it's done that, we've pretty much have a fully functioning assembly. We go back to our main script, and from here, we add the point mass to the assembly. So as I described earlier, we have like a payload. Instead of having like an arm manipulating something, we're just going to apply a mass to whatever end linkage is provided in the URDF file. Once we've applied the point mass and we are defining the steps. So if you want to have a dynamic or a static simulation, you have to define the step for that simulation. In this case, we have a dynamic step. using global constants to define our time. In this case, it's going to be 2 seconds. The increment size, basically how many frames you're going to have within that 2 seconds. And then we apply the boundary conditions to the fixed rigid base link elements. You can't apply displacements to a node that you normally would in the model. If you do that, it doesn't recognize the forces that are the reaction forces on the connectors. It just allows the connectors to be kind of free swinging. So you have to apply a specific connector displacement. So I've called out specifically the connector displacement and provided the rotation, which would be 45 degrees. From here, we mesh the parts and then create a history output to plot in this case, the moment at the base connector. We regenerate the assembly just to make sure that the viewport is showing the exact assembly that we've created, and then we save the model. All right, so I'm going to call the script. You have to call it within the Abaqus API. So you have Abaqus CAE. You're going to pass it a script. In this case, it's our multi-body FEA. I am not doing a 3-link. I am going to be doing a 1-link URDF file, and I'm going to call it 1-link model. It looks like it properly created the model. Kind of run through the Abaqus message. Here is kind of all the important things, so you know that you created it correctly. So all the printouts within that build Abaqus model script prints out here, so you know that each stage of the creation was done properly. So here you're only seeing the base link. So let's see if it properly created the assembly. So we have our assembly. It's very straightforward. We have our base link and our one-arm linkage. So in our step manager, it created a dynamic step. So that was done properly. Interaction, you can see that the hinge was applied. So we have that displacement. And here I was kind of, like I was describing, it's a connector displacement. So that's what you see here is displacement rotation. You're actually creating this connector displacement. So it looks like we have our quadrilaterals. It fit some triangular elements in here to complete the mesh. I guess the geometries didn't work out in certain areas. So now that we have a properly meshed assembly, from the script, I didn't have it submit the job. I wanted to do this manually because if there was any issues, I didn't want it to try to submit a job and then throw a bunch of errors anyways. So you can come in here, verify everything looks good, and we can submit our simulation. So the job completed, and I can go here to results and run the video. I pause the simulation so we can look at the history, defined the outputs that we want. Here we have our moment. To show that it works for multiple arms, I will verify an assembly. So here's our assembly. So the job completed, viewing the results. We're going to move this bottom link 45 degrees, and then we're going to move the other link 45 degrees. Animate that, and you can see that it's moving 45 degrees. And because we have mass properties, it's kind of dragging this other linkage, and then now it's swinging this linkage 45 degrees. You can see in this moment plot, it's quite different than the 1-link arm. It's moving with the one linkage, kind of dragging that other link, and then kind of oscillates a little bit more moment increases when it's resistant moment at that connector because that other linkage is moving. Overall, the script works. There are future considerations for the types of materials that you can apply to each beam element and the different types of connectors, but so far it seems to be working properly.